All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Okay, so it's week 7. I know things probably are really kicking into high gear for you guys. I know midterm exams are abounding. Speaking of which, we have our midterm exam. It's not this week. It's early next week. So midterm is planned for Monday, March 9th. Okay. So I have some details about that for you here. So for the exam format, I'm planning to have 4 conceptual short answer problems. Those will be worth about 40% of the points. There will be 3 problems where it'll be basically just like homework 2, homework 3, where I give you a differential equation, I give you a domain, and I want you to write out the finite difference or finite volume equations for it. So that'll be worth 60% of the points. Okay. So there is, I would say, relatively speaking, there is a higher weight on the conceptual stuff because, my feeling has always been that, when you take these classes, like, yes, you learn important skills, but, if you're not practicing it on a regular basis, then it's easy to kind of to forget kind of the intricacies of, how to apply the finite volume method to the Navier-Stokes equations. But what really kind of sticks with you is the conceptual stuff that you learn. And a lot of times, if that conceptual stuff sticks with you, after this class in your careers, then, even if you don't remember all the details, then you'll still be able to go back and look them up. So, I do put a fair bit of emphasis on the conceptual stuff, probably more so than most other instructors, but that's kind of the reason I do that. Okay. In terms of what you can bring for the exam, writing utensil, calculator, those are pretty standard, just so you can write on the exam and just so you can do your calculations. But I also am allowing you to bring 1 8.5 by 11 sheet of notes, and so that's standard kind of printer paper. You can use both sides. You can write it. You can type it. That's fine with me. And before someone asks, yes, you can bring 2 sheets of paper and just write on one side on both. That's okay for me with me too. But no more than 2 sides of an 8.5 by 11 sheet of notes. Okay. In terms of what to study, so I write all my problems for the exams. I write all my problems for the homeworks. So homework 1, homework 2, homework 3 are all great places to start. Now, the problems you get on the exam are not going to be exactly the same as the homeworks, but they are going to be similar style. So I always tell people that if you can work through the homework problems again, if you can get the right answers again without looking at the solutions, then I'd say you're in great shape for the exam. For the conceptual question, I will be posting a study guide. I had meant to actually do that this afternoon, it just kind of slipped my mind. But I will post a study guide after the lecture today, just so you have that for you. Okay. The study guide is essentially just a collection of all the learning objectives that we've been going over in the class. It's mostly just there to kind of help guide your study. Okay, hence the name. And then, last thing you should look at are the lecture notes. So lecture note has all the the information that's going to be on the exam. It's just a lot to kind of go through. But, if you want to see kind of detailed examples, detailed explanations, they're all in the lecture notes. And of course, all the lecture recordings are on YouTube as well. All right. So, but the lecture recordings, of course, are very long to go through. So don't watch the entire first 7 weeks of lecture notes or lecture videos again. Use the lecture video sparingly. So, only go there to look up something if you really want an explanation of a particular topic. Okay. Okay, but yeah, that's the plan for midterm one. Usually, so this is my first time teaching this class, but I am kind of using a lot of material from another class I've taught. Usually first midterm is usually not too bad. Just because essentially, you're just taking these differential equations and you're just writing the algebraic equations for it. So it is very kind of systematic. It's kind of just one method or a couple methods that you just have to know. But you should still practice, and especially you should definitely get some practice with the conceptual stuff as well. Okay. All right. So plan for today. So I was hoping that today would be the last day that we covered concepts for the midterm, but a couple things may spill over to Wednesday. So we'll get as much done today, and then hopefully just maybe the first 15-20 minutes on Wednesday. That'll be kind of the cutoff for the exam. But plan for today is to finish up our discussion for convection problems in finite volumes. Okay. All right. Any questions about the exam or any questions about just anything that we've gone over so far? Okay. Okay. I have a couple more announcements. And so homework 3, I know was originally scheduled to be due this Wednesday. But since we may still be finishing up stuff on Wednesday, I did push that back by a day just to give you an extra day. So homework 3 is now due on Thursday. And I'm going to post a solution for homework 3 on Friday, just so you have for your studying. But just in case we don't finish all the 2D stuff today, then I want to make sure you have an extra day to do it after Wednesday. And then next week, so Monday we're gonna take the exam. But Wednesday, I've been working on this for weeks, but finally I'm ready to kind of do our first open foam activity together. So next week, I think Monday I know will be kind of a stressful day, but hopefully Wednesday will be a day that I think everyone's been looking forward to, which is using open foam for the very first time. Okay. There's a lot to go over. It's why it's kind of taken me a few weeks to kind of develop this. I have 32 pages of tutorial to go through because we're learning Linux and we're learning OpenFOAM at the same time. So we may not finish everything next Wednesday, but whatever we don't finish, we'll spill over to the next month. Okay. So hopefully next week will be, I know stressful because of the exam. Hopefully this doesn't happen next week. But also will be fun as well because we're doing OpenFOAM and Linux for the first time. Okay. All right, so let's go ahead and get started. Okay, so topic for today is we're going to be, continuing our discussion for convection problems in finite volumes. Okay? Specifically, we were still on 1D problems. Okay. All right, so let me just kind of give you a refresher in terms of, what we were doing. So a 1D convection diffusion equation looks like the following, right? So essentially, we just have an ordinary differential equation with some convection in there, right? So our equation looks like this. So we have d dx of u times p minus k d dx of d phi dx is equal to q of x. Okay. All right. So our convection term is this first one, of course. Okay. Our second term here that involves the k. This is our diffusion term. Okay. And then our last term here, this is our source term. Okay. By the way, hopefully I apologize. I have no idea what's going on next door. What's up?
The wind tunnel is on.
The what?
The wind tunnel.
Oh, the wind tunnel?
Yeah.
Oh, but why? Why now? So hopefully on Zoom it's not too bad, but you know I'm kind of shouting at the top of my little Asian boy lungs here. Okay. So of course the new thing that we're seeing here is convection, right? And in particular, you know, U here, this is our convection velocity. Okay. Where remember, the whole idea with convection is that convection is the active transport of our medium or material through some kind of flowing velocity, right? So that's exactly what U is here, right? And so remember, in finite volumes, you know, so this is not the first time we've seen this equation. So we've seen this equation in finite differences. But of course, the difference now is that we're working in finite volumes, right? Where we are basically integrating our equations across a cell, right? Okay. And then so by integrating, remember, we are able to make use of all of our integral properties. So things like, you know, divergence theorem to reduce the order of the derivative there, which is always important. Okay. And what we end up with is the following, right? Right. So the details of this derivation, you know, were there from last time, so I'm not going to repeat it. But essentially, we end up with the following equation. So when we integrate the convection term, we get U times phi evaluated at x, evaluated on the east face, okay, minus phi evaluated on the west face, okay, minus k multiplied by the derivative evaluated at the east face minus d phi dx evaluated on the west face, okay, is equal to q of x delta x, or q of xc, I should say. Okay. Well, remember, you know, I'm using lowercase letters here for the east and west phase because those are the you know, solution values evaluated at the edges of our finite volume cell, right? So phi E is evaluated here, and phi little w is evaluated there. Okay. Okay. So essentially, you know, when we evaluate our integrals, we're evaluating all the diffusion and convection terms at the edges of our finite volumes. That's kind of the consequence of the divergence theorem. Okay. But kind of the central conundrum with a lot of finite volumes is that, you know, we don't want to compute our solution values at the cell faces. We want to compute them at the cell centers. Okay. So this is phi C, and the neighboring one phi sub E, and the other neighbor one phi sub big phi sub big W. All right. And so the game that we play with finite volumes is how do we estimate these space values, you know, based on the self-centered values. Ooh, I can smell the wind tunnel. Okay. So, you know, there's a variety of strategies that we can do, right? So we've talked about, you know, for at least for the diffusion terms, we use our finite differences, and so we just basically just take the difference of the self-centered values. We divide it by the grid spacing. Okay, there's not much ambiguity there. That's, you know, we kind of always do the same thing with diffusion. But with convection, remember, you can either pick a central scheme where, you know, the face value is just the average between the two neighboring ones, or we pick an upstream scheme. So that's kind of what we did last time. Okay. Okay. All right, but we won't go through that again. Okay. But that's kind of essentially kind of what we did. Right. So where I want to start today is a topic that we didn't get to last time, which is how do we do boundary conditions for finite volumes in situations where we have convection. Okay. I feel like I can think again, but that's okay. Okay. All right. So remember, there are two types of boundary conditions, and so there are Dirichlet and Neumann boundary conditions. So we're going to go through both. Okay. Let's start with the Dirichlet boundary conditions. Okay. So remember, Dirichlet boundary conditions directly specify the value of our solution phi at the edges of our domain. Okay. All right. So let's do an example to see how this is done. Okay. All right. So let's say that we have our cell here. Okay. So this is our phi sub c. Okay. And then on the left-hand side, we have a Dirichlet value. So we'll say phi is equal to phi naught here on the left-hand side of this. Okay, so we have a Dirichlet boundary condition on the west edge. Okay. And then on the right-hand side, we have a neighbor, right? And so our neighbor there is still phi sub b. Okay. So on the right side, nothing's going to change, but on the left side, we do have to make modifications according to that Dirichlet boundary. Okay. Okay, so I'm going to write down our equation from up here. This is as good a starting point as any. Okay. So let's start with u phi sub big E minus phi sub little w minus k d phi dx on the east edge minus d phi dx on the west edge is equal to q at xc delta x. So when you're applying boundary conditions, and we'll go over the 2D case as well, this is always going to be your starting point, right? Remember, it's kind of the same thing as our diffusion with finite volumes, where just because there's so many different scenarios and so many different ways that boundary conditions can be applied, it's always important to know how to go based off this equation rather than just plugging into an equation that we've kind of seen before. Okay. Okay. So for this situation, on the east side, nothing is going to change, right? And so we can evaluate our east terms the same as before, right? So that's phi sub little e here, okay, and d phi dx on the east edge, okay? So phi sub little e, right? We're just going to use a central scheme here, so we're going to assume that we don't need an upwinding. So phi sub little e here is going to be the average of phi sub c plus phi sub big E divided by 2. Okay. Right. So remember that was our way to kind of centrally approximate the face values. Just simply take the average between the two. Okay. And then d phi dx here, this is simply going to be phi sub big E minus phi sub c all divided by delta x. We just use our standard kind of finite difference approximation for that derivative. Okay. So that's all well and good. Okay. So east edge, no change. On the west edge, this is where we do have to make differences. Let's start with the diffusion term, just because we've seen this one before. Okay? So for the diffusion derivative, we're again going to use finite differences, but we're only going to travel across that half cell because, that's how far we need to go to get to the Dirichlet boundary condition. So this is going to be phi sub c minus phi naught, which is the Dirichlet value, divided by the distance we travel, which is delta x, divided by 2. Okay. All right. Now for the value of phi sub little w. Well, this one's actually very straightforward because, the value of phi on that west edge is directly given to us, right? So there's no approximating that we have to do. We just have to kind of plug it in, right? And so this is going to be exactly phi naught, which is the value of the Dirichlet condition, just because we know that. Okay. All right, and so now that we've approximated all the face values, so everything is either in terms of the self-centered values or the boundary condition, we can just go ahead and simplify. Okay, so remember anything that's known, basically any phi naughts, we're going to move over to the right-hand side, and all the unknowns, the self-centered value, we're going to keep on the left. Okay. I'm just going to do that in one step, but you can do this in several steps, but just for the interest in time. Okay. So we do that, we get coefficient of u divided by 2 plus 3k divided by delta x times phi sub c, okay, plus u divided by 2 minus k over delta x times phi sub big E, okay, is equal to q at xc times delta x plus u phi naught plus 2k phi naught divided by delta x. All right, so that there is our finite volume equation for a Dirichlet boundary condition on the left-hand side for 1D convection diffusion. Okay. Now, like I mentioned, this equation is going to change. So the signs of the terms on the right, they're going to change if our Dirichlet boundary condition is on the other side. So just be aware. Okay. Any questions on this? Okay, good. All right. So we've done this a few times now. So hopefully the process is becoming clear. Okay, so now let's do the Neumann boundary condition. This one's a little bit more tricky, okay, just because our new convection term here does not have a derivative. Okay, so let's recall, what Neumann boundary conditions are. So Neumann boundary conditions specify our solution derivative on the boundary. Okay. So again, let's do an example just so you can kind of see the whole process in action. Okay, so this time we're going to do a Neumann boundary condition on the right. Let's see. Okay, so on the right-hand side, we'll say here that d phi dx is equal to gamma. Okay. And this right here is our central cell, so this is phi sub c. And then on the left-hand side, we have the west neighbor phi sub w. Okay. Okay, and then once again, let's start with our general equation after we've applied our finite volume method. So we have u times phi sub little e minus phi sub little w minus k d phi dx on the east side minus d phi dx on the west side is equal to Q at xc times delta x. Okay. So what we previously did, so if you think back to when we did finite volumes with diffusion, right? We had a Neumann boundary condition. Since we said that the Neumann boundary condition is a condition on the derivative, we looked at our derivative term, or we looked at our diffusion term and said, hey, we have a derivative here, right? So all we did for the diffusion case, because we only had to replace just this derivative term, was we said that, hey, let's just take our Neumann boundary condition and just plug it in for that derivative. Okay. And then everything is good for the world because there's nothing else we can plug in. Okay. Now, but for convection, we kind of have an issue because we also not only have the derivative term, but we also have our convection term, which is just phi just by itself, no derivative. So for a situation where we have a condition on our derivative, what do we even plug in for the solution value itself? Right? Because the answer there is not super obvious just because we don't have any information for what that v sub little e is there. And we have no neighbor to the right? So there's nothing beyond that boundary. So it's not like we can estimate it based on neighboring values, right? We could do an upwinding case, and so we could estimate this as phi sub c, but that wouldn't be completely accurate either, especially if the velocity is going from right to left, because the velocity was from right to left, and it doesn't make sense to plug in phi sub c there, because that's in the downstream direction. There's no downstreaming method. There's only upstream or upwinding methods. Okay. So how do we deal with this? So let me rearrange these terms, right? Because right now we've kind of separated the terms in terms of convection and diffusion, but let me separate them in terms of east side and west side. Okay, so on the one hand we have u times phi sub e minus k phi dx on the east side minus same thing on the west side. So we have u phi little w minus k phi dx on the west edge is equal to q xc delta x. So all I did was I just kind of rearranged the terms. So in one square bracket, we have everything that's happening on the east edge, and on the other square bracket, we have everything that's happening on the west edge. Okay. Now, on the one hand, just because we have a west neighbor, we can go ahead and plug in, right? So for phi w here, we know this is equal to phi sub c plus phi sub big W divided by 2. And then for the derivative, we have phi sub c minus phi sub big W divided by delta x. Right? And so in some sense, it becomes a bit easier just because, we're just dealing with east and west side. So you can definitely do this for every problem and just, organize it by east and west. Right? That's essentially what we do in the 2D problems too, is we break it down to north, south, east, and west. Okay? So we're just kind of applying that same. Okay. Now, the reason I did this is that, one way to kind of interpret this is that if you look at this entire term here, one way that we can interpret this is that this is the exact transport of our phi, of our solution value phi, across that east interface. Because what we're saying in these equations is that our solution phi can be transported either by diffusion or convection. Okay. And so by kind of grouping these terms together, we're saying that this represents all the transport of phi that can occur. Okay. Now, if we reimagine, so we kind of reimagine and kind of recast our Neumann boundary condition, right? Right. So mathematically, a Neumann boundary condition, typically is used to represent the solution derivative, right? But another way that we can represent this is that we can say that this gamma here, right? This gamma here represents all of the transport or all the flux of phi that occurs across that boundary. So traditionally, this is how we usually interpret things in a fluids perspective, because you'll see that when we do open flow, there's no Dirichlet boundary condition, there's no Neumann boundary condition. We do things like pressure boundary condition, velocity boundary condition, things like that. Okay. And so, if we kind of look at this from a more practical perspective, then we can say that this gamma represents transport, not necessarily a derivative. Okay. And so we can make use of that fact and then kind of just use that here, where we can say that, if that gamma, right, if that gamma instead represents all the transport of phi across the boundary, then we can say that this entire quantity in the square brackets is represented by gamma. So we're no longer just replacing just a single derivative or a single term, or replacing an entire expression, because that expression represents the flux. All right, it's a little bit cheating, I know. And so it kind of feels like we're kind of moving the goalposts a little bit just to not deal with the problem that we don't want to deal with. And to be fair, and to be honest with you, there is a way to deal with this where you can estimate that base value using a Neumann boundary condition, and there's a way to do it. It's just very kind of cumbersome, and to me, it doesn't really add much to this class to kind of go through that intense mathematics. Where most of the time this is a very fair assumption. This is a very kind of a good assumption to make. And it doesn't really lead to that many errors. Okay. Now it is convenient because now we can recast our equation, right? So we just replace that entire thing by gamma, right? While the other terms stay the same. So we have minus u times phi sub c plus phi sub w divided by 2 minus k phi sub c minus phi sub w divided by delta x, okay, is equal to q at xc delta x. Okay. Now our equation is super simple because now that gamma, we just move it over to the left-hand side, okay? And the other terms we just kind of rearrange like we usually do, right? And then we end up with the following equation, right? And so we get minus u divided by 2 minus k over delta x times phi sub big W plus minus u over 2 plus k over delta x times phi sub c is equal to q at xc delta x minus gamma. All right. Any questions on how we got that result there? Okay, so we're going to use that trick again in 2D because in 2D it gets more complicated because we have 4 phases instead of just 2. So whenever you have a Neumann boundary condition, you essentially just replace that entire phase integral with that Neumann condition. Okay. All right. So in general, Neumann conditions and finite volumes, much easier to deal with than traditional conditions. Okay. All right. So there is an example in the notes with numbers for 1D problems, but I think we went pretty much in pretty good detail here. So I'm going to skip that for now, but just know that if you do want to see a 1D example, there is one in the lecture notes for you. Okay. But I am going to skip ahead a little bit just for the sake of time. And so let's talk about 2D convection with diffusion with finite volumes. Okay. All right, so for 2D problems, we're going to start with our convection diffusion equation 2D, and just like before, we're going to integrate it. Okay, so let's start with that. So first, we have our entire equation here in vector form. So we have divergence of the product of u divided by phi minus k times the divergence of the gradient of phi is equal to q at x comma y, right? So everything is in 2D now, so everything is a function of x and y, right? Where again, this right here, this is our convection term. This right here is our diffusion term. And this right here is our source. Okay. Okay, so let's go ahead and integrate this across our two-dimensional cell. Okay, so we're going to integrate every single term here. All right, and then just like we did for the diffusion equation, every single term on the left-hand side, everything with the divergence, we're going to apply divergence theorem to them. So divergence theorem. And then here also divergence theorem. Okay, so remember what that's going to do is that it's going to turn those area integrals, it's going to turn that surface integral into a line integral around the boundary. Okay. And so what we get from that is line integral around the boundary of phi times the dot product between the velocity and the normal vector. Okay, ds minus k, line integral around the boundary of gradient of phi dot product with the normal vector ds. And on the right-hand side, we can't do anything with the source terms. We just keep that double integral there. But remember, we are going to use trapezoidal rule to evaluate that integral on the right-hand side. Okay. All right, so remember, once we kind of get to this point, our line integrals here split into 4 integrals. So we have a separate line integral for each side of our square cell. All right, so let me go ahead and draw our cell again here. All right, so we have our east face, our north face, our west face, and our south face. Okay, where each of them, remember, has its own normal vector. Okay. And we are integrating across each edge here. Okay, so we're just integrating just around the outside. Okay. So remember the key here to evaluating our line integrals here is that we are taking the dot product between a specific quantity and the normal vector on each face. Okay. All right, so previously for diffusion, we only had one term we needed to take the dot product of, which was just the gradient. That one is still there, but now we also need to take the dot product between the velocity vector and the normal vector as well. Okay. All right, let me write in all the normal vectors here just so that you can see. So on the east face, we have 1, 0. On the north face, we have 0, 1. West face, we have 0, 1, negative 1, 0. And on the south face, we have 0, -1. Okay. And then the vector quantities that we are taking the dot product of are, one is the u velocity, so that's u, v, velocity in the x direction, velocity in the y direction, u and v. And we have the gradient of phi, which is partial phi partial x in the x direction and partial phi partial y in the y direction. Okay. All right, so remember, we're going to evaluate each face individually. Okay, so let's go one by one on each face. Okay, so let's do the east face first. Okay, so we have integral on the east face of, right? So just like I did for the Neumann boundary condition, I'm going to combine both the convection term and the diffusion term in one integral because they're both essentially the same. Okay, so we're taking the integral on the east face of phi times u dot product with n minus k gradient of phi dot product with n ds. Okay. So first, let me plug in for all the vector quantities here. So u, gradient of phi, and n. Okay. So doing that, right, we still have our integral here. We get phi, right? So we're taking the dot product of this u velocity vector and the normal vector on that face, right? So u, v, dot product with 1, 0. All we're left with for that is just u, okay, minus, same thing for the gradient. So we're taking the dot product between the gradient vector, which is partial phi partial x, partial phi partial y, and the normal vector, which is 1, 0. All that leaves us with is partial phi partial x. This is minus phi or minus k times partial phi partial x. Okay. All right, so let's go ahead and evaluate this integral using the trapezoidal rule, right? So remember, we're integrating across this entire edge right here, right? So remember, the way that we do that is just we evaluate the integrand at the centroid. So we're going to evaluate everything at the center of the east face, and then just multiply by the length of that edge. Okay, so if we do trapezoidal rule, what we get is phi sub little e times u minus k times partial phi partial x on the east face multiplied by delta y. Okay. And so all the other integrals, the north integral, the west integral, the south integral, they're all going to look the same. Okay. But before we kind of get to those, are there any questions on how I got this result here? Okay. All right. So let's do the same thing for all the other faces, but we'll go a little bit quickly just because of time. Okay. All right. So let's do the north face now. Okay. So we have integral on the north face of phi u dot n minus k gradient of phi dot n ds. Okay. So we're going to follow the same process here. The only thing that's different is that on the north face, the normal vector is different, right? So on the north face, our normal vector is 0, 1. Okay. So that's going to change, what result we get from the dot products as well, right? And so if we do that and we apply our trapezoidal rule, we get V sub big N times V minus K partial phi partial Y on the north face multiplied by delta X. Okay. All right, so now we're basically picking out the Y components of each of our vectors. So Y component of the velocity, Y component of the gradient. Okay, let's do the same thing on the west face. We have integral on the west edge, B times U, dot product with N, minus K, gradient of phi, dot product with N, ds. Okay. Where now our normal vector on the west face, this is minus 1, 0. Okay, minus 1, 0. Okay. Right, so be aware of the minus sign, right? So don't forget that. And so we do that, we get minus phi sub little w times u plus k partial phi partial x on the west face multiplied by delta y. And then finally, we have the same thing on the south face. So we have south face here, integral on the south face times phi u dot product with n ds minus k gradient of phi dot product with n ds. And now we need 1 ds. I apologize there. Okay. Okay, and then finally on the south face, our normal vector here is 0, minus 1. Okay. All right, so we plug all those in. We take the minus sign into account, and then we end up with the following. So we get minus phi sub little s times v plus k partial phi partial y on the south face times delta x. All right, so those are the four base integrals. And so, if you want your finite volume equation, you would just simply add all these together. So doing so adding all of those equations together will give you one single expression for the finite volume equations. All right. Any questions on this? Okay. All right. So, of course, at this point, we do have our conundrum, right? So remember, all of these phi values that we have here, they're evaluated at the faces, but we want to put them in terms of the self-centered values. Okay. And so we're going to apply our normal kind of approximation rules for this. Okay. So I'm not going to write out the whole equation again, but I am going to show you, typically what's done. Okay. So we have phi sub little e, phi sub little n, phi sub little w, phi sub little s. Okay. So these are all the phi terms that come from the convection term. Okay. So remember, convection, we just end up with phi just by itself. Right. So under a normal scheme, right? So let's say that we have a Peckley number less than 2, and we can use our central scheme. Then we just use the simple averages between these and its supposed neighbor. So phi sub little e, this is going to be phi sub c plus phi sub e divided by 2. Okay. Phi sub little n is phi sub c plus phi sub big N divided by 2. Phi sub little w is phi sub c plus phi sub w divided by 2. And then phi sub little s is phi sub s plus phi sub c, all divided by 2. Right, so that's kind of our standard second order, second order approximations. Okay. Okay. Now, of course, this is assuming that we have a stable solution, but of course, if we have to do some upwinding, then that will change this. Right? And so if we need to, so let's say the Peckley number is large, then we can apply upwinding to alter these values. Okay? But these are kind of the base case when you have a stable situation. Okay. All right. So let's go ahead and then apply the same thing for all the derivatives. Okay. So you have d phi dx on the east edge, d phi or partial phi partial y, excuse me, partial phi partial x, partial phi partial y. So we have partial derivatives now. Okay. All right, so let's go ahead and plug all these in. Remember, for these, we just use a simple finite difference between the two neighboring cells, right? So on the east edge, we have phi sub big E minus phi sub C, all divided by delta X. On the north edge, we have phi sub big N minus phi sub C, all divided by delta Y. On the west edge, we have phi sub C minus phi sub big W, all divided by delta X. On the south side, we have phi sub c minus phi sub s, all divided by delta y. Okay. Okay. All right. So last thing to do. So now that we have expressions for all of the face values, right? So everything is in terms of self-centered values here. All that's left to do is just plug all of these back into our integrals, add them all up together, and then simplify. Okay. Now, of course, the fact that we have, expressions for all of these just means that, we're assuming that we have neighbors on every side. And so the equation that we get from this is our equation for an interior cell, which has neighbors on all four sides. Okay, so that's eventually what we're going to do. And remember, for interior cells, you can just apply this equation straight up, right? Because every interior cell, their neighbors are obviously different, but they all have the same neighbors, and so they're all going to follow the same behavior. So remember, like I said, for interior cells, you don't have to go through this derivation. This is kind of just for your understanding and kind of your knowledge. For interior cells, you can just kind of fit it into this pattern, fit it into this stencil. Okay, so let's go ahead and plug those in, right? Okay, so I'm going to go integral by integral, and then I'm going to separate them by square brackets. Okay, so let's start with the east integral. So for the east integral, we have p sub c plus p sub e divided by 2 multiplied by u. Okay. Minus k phi sub e minus phi sub c divided by delta x. Okay. And then for each integral here, I am going to apply the trapezoidal rule right away. So that means in order to evaluate this, we just simply multiply by the length of that side, right? So this is going to be delta times delta y. Okay. So this right here is our east integral. Trapezoidal rule applied. Okay. All right, so let's do the same thing for on the north side. So on the north side, we have something very similar. So we have phi sub c plus phi sub big N divided by 2 multiplied by v minus k phi sub n minus phi sub c all by delta y all multiplied by delta x. Okay, so this right here is our north integral. All right, so let's do the other two integrals now. So we have a plus square bracket phi sub, so this is going to be the west integral. So phi sub w, or we need a minus sign there. Sorry. Right. So remember, for the west and south integrals, we have that minus sign that kind of flips the sign of everything just because of the normal vectors of the set. Okay. So minus sign multiplied by phi sub c plus phi sub w multiplied by 2 multiplied by u plus k phi sub c minus phi sub w divided by delta x, whole thing multiplied by delta y. Okay. Okay, so that right there is our west integral. And then finally, we have our south integral. So very similar here. So we have a phi sub s plus phi sub c. Got the minus sign again. Sorry about that. Okay, so minus sign phi sub c plus phi sub s divided by 2 times v plus k phi sub c minus phi sub s all divided by delta y all multiplied by delta x. Okay. And so that right there is a contribution from the south, Okay, and then of course, all this is equal to the right-hand side. We did not forget that. So this is q at xc comma yc multiplied by delta x, delta. Okay, so it's a doozy, right? So it gets very not too difficult. It's it's basically just the four thing, just four same thing, just multiplied by 4 times. It's just there's just a lot of terms and a lot of things to kind of keep in mind. Okay. So with these kind of 2D convection diffusion equations, the most important thing is just to stay organized, right? So you'll see this, and so the very last problem in homework 3 is a problem just like this essentially. So I give you a 2D convection diffusion equation, and I tell you, give me all the finite volume equations for these cells. And so the main thing is that you just have to kind of stay organized. That's the only way to kind of get through these things. Okay. Now, the last problem in the homework, it is a bit more challenging because you do have to make a decision on whether you want to apply upwinding or not. Okay, so remember for this equation here, we did not assume any upwinding. But for the homework you do. Okay, so that is going to affect how you do this. Okay, so last thing that we have here is that we just need to simplify. So we're going to group the like terms together according to the different phi values. All right, and then we end up with the following expression here. So we have first the coefficient for phi sub big E, right? Oh, and I'm also going to make the assumption that our grid spacing is uniform. Okay, so that's what we usually do in 2D problems. So we're going to assume that delta x is equal to delta y. And so I'm just going to use a delta for that. Okay, so just a single triangle to express the grid spacing. So this is u times delta divided by 2 minus k, all multiplied by phi sub big E, okay, plus v times delta divided by 2 minus k times phi sub big N, plus minus u delta divided by 2 minus k phi sub big W, plus minus v delta divided by 2 minus k bs, plus 4k b sub c is equal to q at xc comma yc delta squared. So this expression right here, this is our finite volume equation. For 2D convection diffusion. Okay. Wait, we're not done, right? This title was not done yet. So this is assuming no upwinding and interior cell. Okay. So very, very long title for a very, very long equation, right? But remember, for these finite volume equations, you have to be kind of specific. So, again, for certain situations like interior cells, you could just apply this equation and just kind of plug in the different phi values here. But even for this, you have to be careful because if you do have to use upwinding, then you obviously can't use this equation here because the upwinding is going to change the coefficient on the convection terms. Okay. So this is kind of the base case, simplest case where we have no upwinding and we have a neighbor on every side. Okay, so in those cases, you can just plug into this equation. All right. Any questions on how we got this equation here? Okay. All right. So I think for the last 15 minutes of class today, I think just like today, I think we'll get into the boundary conditions and we'll do an example for that next time. But I do want to talk a bit about how things would look different if you do have to use upwinding. Okay. So this is not strictly part of the lecture notes. It's kind of just implied based on our earlier discussion on upwinding. But since the homework problem is a 2D problem, convection diffusion, and it doesn't tell you in the problem, but I'll spoil it for you. You do have to use upwinding. I want to kind of show you what that. Okay. All right. So when do we use upwinding? So remember, we use upwinding. We generally prefer not to use upwinding just because it does, well, first of all, it just makes things a lot more complicated. And second of all, it does lower our accuracy, right? So generally we do prefer to use the central scheme because it is more accurate. But if our Peckway number, okay, which remember the way that we compute the Peckway number is we take the product of the velocity multiplied by the grid spacing divided by k. Okay. And so if this is greater than 2, okay, then if we use a central differencing scheme, so if we use a central scheme for the convection terms, it will lead to an unstable solution. So while we normally don't want to, sometimes we just have to, because a stable inaccurate solution is 100% more preferable than an unstable solution, because an unstable solution just looks like garbage, and you will be laughed at by many people. So you always want to make sure your solutions are stable. Okay. Okay. So if you're in a situation like this where your grid, you can't really do anything about your grid spacing, you can't really do anything about the parameters, so you have no choice but to use upwinding. This is how you would do it in 2D. Okay. Okay. So in 2D, remember you have two different velocities, right? So you have a velocity in the x direction and a velocity in the y direction. So you have to consider their upwinding properties separately. Okay, sounds good. All right. Okay, so in 2D, remember you have to consider the x and y velocities separately. Okay. Okay. So for the x velocity, right? Remember, our x velocity is u, right? Not u, the letter u. Now, depending on the sign of u, that tells us which way the velocity is going, right? And so if u is greater than 0, right? U is greater than 0, right? In other words, we have a positive x velocity. That means our x velocity is going from left to right, okay? That means when we do upwinding, we want to put more emphasis on the left side. Okay. So, for the x velocity, there are basically two face values here that we have to kind of take into account. So there's phi sub little e and phi sub little w. Okay. Okay. And remember the question for upwinding is, how do we estimate these based on the self-centered values? Okay. So for a positive velocity, phi sub little e, right? If we're going from left to right, we're going to take the one on the left-hand side of that edge, right? Right, and so let me go ahead and draw our cell here one more time. So this is phi sub c, this is phi sub e, phi sub w, phi sub n, and phi sub s. Okay. Okay. So if our velocity is going from left to right, that means for this phi sub little e here, okay, we're going to pick the one on the upwinding side. So in that case, that's going to be phi sub c. Okay. So again, no averages, no divide by 2, anything like that. We just pick the side where the velocity is coming from, which is the left side. Okay. Now for phi sub w, right? Phi sub little w, we're going to pick the one on the left side. And so that's going to be phi sub big W, right? So phi sub little w, that sits between phi sub, big W and phi sub C, right? So we pick the one on the left side, which is phi sub big W. And I try to emphasize that W because little w, big W, they look the same. So, you pick the one on the side. Okay. Versus for a negative velocity, right? And so in this one, we're going to emphasize the right-hand side. So that means for phi sub little e, the quantity that's on the right-hand side or the self-centered value on the right-hand side, that's phi sub big E. Okay. And then for phi sub little w, the self-centered value that's on the upstream side here is phi sub c. Okay. So I think the thing that gets confusing for people in 2D is that in 2D upwinding is that, when you're considering the x velocity, it doesn't really affect the values of phi sub little n and phi sub little s, because those are basically neighbors and integrals on the vertical side. Okay, so when you're considering the x velocity, only look at just the x integrals, which are just the little e and little w integrals. Okay. Now, where this comes into play, right? All right, so let me just kind of scroll up here a little bit, right? So unfortunately, if you are going to have to do upwinding, then you kind of have to start from this point right here, okay? And so for these terms right here, right, so I'm going to highlight this one here and this one here. You would basically replace these two terms here with their corresponding upwinding terms, right? So let's say that, for the sake of argument here, that we had a negative velocity, right? And for negative velocity, we don't plug in the central scheme. We don't plug in the average. We just plug in their upwinding values here. So for this one, for the east integral, this would be phi sub big E. And then for the west integral, this would be phi sub big C. Okay. So it does simplify the math a little bit. So there's a little bit less to simplify afterwards, but I think it's one of those things where it's easy to kind of trick yourself in your head, or not really trick yourself, but just kind of get lost in the sauce. That's what I say. Because there's a lot of details and a lot of little kind of things that you have to kind of keep track of at any given time. Okay? Especially if you have one velocity that's positive, another velocity that's negative, and so you have to think, okay, which direction do I have to go for this? Okay. And then let's do the same thing for the y velocities here. So for the y velocities, if v is greater than 0, right? So if v is greater than 0, that means our velocity is going from the bottom up, right? So it is going in the positive y direction. And so that means we want to emphasize, if I can spell, we're going to emphasize the bottom direction. I should just say south. Okay, and this is only going to affect the integrals in that y direction. So it's only going to affect the value of phi sub little n and phi sub little s. Okay, so if we're coming from the south side, that means for phi sub little n, we're going to approximate this with phi sub c. And then for phi sub little s, we're going to approximate this by phi sub big S. Okay. And again, I drew the S big to emphasize that this is the self-centered version. Okay. All right, and then finally, if we have a negative y velocity, v is less than 0, that means we're going to emphasize the north direction. So that means we're going to estimate our face values according to whichever neighbors on that north side. Okay. So we have phi sub big N is equal to phi sub big N, and then phi sub little s is equal to phi sub c, the central cell. Okay. Okay. And so going back to our equation up here, right? So again, that's going to affect this value here, this value here. Okay. So let's say for the sake of argument, let's say we had a positive y velocity. So let's say that v is greater than 0, and we needed to apply upwinding. Okay. And so for the north integral here, we're going to replace this with phi sub c. And then for the south integral here, we're going to replace this with phi sub s. And then you just continue with the simplification just from. Okay. Any questions on upwinding in two dimensions for fine volumes? Okay. Now, like I said, upwinding is not preferable just because it does lower our accuracy. So, that kind of begs the question is there a way to do upwinding and still retain our second order accuracy? Okay. Because that would be the best of both worlds, right? So then we get the stability properties of the upwinding and the accuracy properties of the central scheme. Okay. And so fortunately, the answer is yes. Okay. Right. So that seems great. So why haven't we been using that this whole time, right? So why are we bothering with these methods that are not as good? Well, you'll see why on Wednesday. So on Wednesday we will go over the final kind of topic for finite volumes, which by the way is not going to be on the midterm. So I'll kind of cut it off at a certain point. You'll see why it's not a term. Okay. So on Wednesday we're going to go over a very famous method in CFD called the quick scheme. And it's not quick in the sense that it's fast. In fact, it's the opposite of fast. It takes a while to kind of explain. But quick there is an acronym. And so it stands for quadratic upwinding interpolation for convective kinetics. And you'll see you'll kind of learn in the second half that CFD people, they love their acronyms. There is an acronym for everything. And it makes it kind of seem like a really fancy club with all these acronyms. Like, oh, are you using DNS? You're using LES. Like, oh, I'm using RAND. So CFD people love their acronyms, and so you'll feel like a genius, once you know all these acronyms. But before that, it's really okay. Okay. Any final questions before we wrap it up for today? Okay. All right. So as I predicted, a little bit of 2D convection is going to spill over to Wednesday. So Wednesday we'll spend the first 20 minutes. We'll finish this up. We'll talk about boundary conditions. We'll do an example, and then we'll finish off talking about the quicks. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Wednesday. Sure. Right.
So I don't homework 2 and homework 1.
I don't think I posted a solution
You
yet.
have, because I was double checking.
Yeah,
It's like,
I will post solution to homework 1, homework 2 today, and then homework 3 solution on Friday.
yeah, okay. Maybe that makes sense. I just wanted to double check, because I was like.
Yeah, I did it for my other classes, but not for this week, so I need to. Yeah, thanks for reminding me.
But on the boundary, the edge is smaller. I think I know. Because between the boundary and the C and the is small. Yeah.
I don't know, because this class is going to be taking the place of 417.
Oh, is it?
Yeah, so because a lot of this content right now is 417, but this is like 417 plus. And so the only difference that 417, I go through the math lab. So we would actually be implementing all the methods. But I think the plan long term was for this to replace that 417. Because I think practically speaking, like OpenFOAM is more valuable as a skill than the methods.
Got it. Okay.
Study guide, you said you'd be putting answer responses in there.
Yes.
Just problem wise, just go to 1, 2, 3.
Exactly, yeah, so there wasn't really any problem with homework 1, so the problem would be homework 2, homework 3.
Okay.
Yeah.
Homework 3, you said you changed the due date from Wednesday to Thursday.
Yeah.
So Thursday night, you'll be releasing the answers or.
I'll probably put the solution Friday morning.
Friday.
Yeah.
All right.
Because I won't be awake. Thank you. Yep.